Okay, welcome everybody to the online series of seminars on the topic of tunneling in QFT and also beyond. This is a series that we're running together with Oli Gould and Andreas Eksted. And it's a series of talks, roughly one per month, that takes place on Thursdays at 2 p.m. Uh, well, if you're interested, you can go on Indico and check out the previous talks. And we have a dedicated YouTube channel where all of these talks are recorded, so people can go and check them out afterwards. So today we have the 10th talk in the series, and it's going to be given by Professor Mark Hindmarsh, who's a professor at Sussex, but also a professor at the University of Helsinki. So he's an expert on numerous topics. He's been working on physics of the early universe for quite a long time and has published many important works, especially on the topics of phase transitions, gravitational wave production, axion string networks, and such. So today, it's a pleasure to have him give us a talk on cosmology and the AB transition in the superfluid helium-3. So go ahead, the floor is yours.
Okay, thank you very much for that kind introduction, and thanks also for the invitation. Very interesting topic for me, this series, and I'm happy to be able to present to you some aspects of work that I've been doing, which is perhaps maybe not so familiar to early universe cosmologists, but it is something that I've been interested in for a long time, and that's the relationship between the kind of things we study for phase transitions in cosmology and a real phase transition, which is the AB transition in superfluid helium-3, which I'll talk about in the second half of the talk. But in the first half of the talk, I'm going to sort of set up the situation in cosmology in a sort of a summary, and then motivate why we would turn to superfluid helium-3 to tell us something about cosmology. So the idea that there might have been phase transitions in the early universe is a long-standing one. Kind of arises from the observation that in the standard model, the state of matter in the universe might have changed as we work our way, say, backwards in time. So at temperatures of around 100 MeV, times of around a few tenths of a millisecond around after the Big Bang moment itself, then quarks and gluons emerge from the sort of as hadrons are squashed together and kind of melt. And still earlier in time, about 10 picoseconds after the Big Bang, temperatures of 100 GeV, then we see that the electroweak symmetry becomes manifest. Elementary particles become massless, and W and Z particles become the same as photons in some sense. And then even earlier in time, well, that's about as far as we know for sure what happened, but there might well have been new symmetries emerging and new interactions. And in these changes of state of matter, as we work our way back forward again, we might have seen departures from equilibrium and homogeneity, which are sort of fundamental assumptions behind Big Bang cosmology. And particularly if the transition was a first order phase transition. So there it would have preceded by some kind of relativistic analog of condensation, or reverse boiling, or a fizz as you release the pressure on a bottle of soda water. You can also get departures from equilibrium and homogeneity if you make topological defects, and that can happen at any kind of transition. So, for example, you can make a Abrikosov vortices, analogs, cosmic strings, in a transition, early universe transition. But the reason for thinking about first order one reason for thinking about first order transitions is that a departure from thermal equilibrium, a strong departure from thermal equilibrium, is required to make the baryon asymmetry that we see in the universe. And those departures from equilibrium and homogeneity can also generate gravitational waves and a stochastic gravitational wave background. And this was realized, I guess, yeah, it's coming up for the 40th anniversary of the paper by Witten, which pointed this out in the context of the QCD transition. So then, supposing there were a first order transition in the early universe, what would have happened? Well, it would have proceeded, we think, by by nucleation of bubbles of the low temperature phase. They expand and merge, and eventually the stable phase, low temperature phase, takes over. Now, this animation that you can see shows the kinetic energy in a fluid simulation, which I'll talk about a bit more later on. And the sort of the hot-looking regions are regions where the fluid is moving, whereas the cold-looking regions of the fluid is stationary. So these expanding bubbles have perturbed the fluid. They've generated pressure shells as they expand. By now, the transition has completed, and what's left over is a bunch of pressure waves, i.e. sound waves. And these sound waves are making gravitational waves. And the particular spectrum of the gravitational waves has information about the phase transition itself. So in particular, things like latent heat or some, wall speed, the time it took the transition to happen, and so on. I'll talk about a bit more about those in a moment. So if a phase transition in the early universe made a gravitational wave, what frequency should we look? Well, here's a sort of back of the envelope calculation that you can do by in the standard cosmology by translating temperature to time and also to redshift. The time of the phase transition happens tells you the lowest possible frequency that it could have, and then you redshift it to today, and you find that the QCD transition would produce waves with periods of at most a year, and possibly quite a lot less, depending on how quickly the transition took, how quickly the transition happened. In fact, the period of the waves is more closely related to the time it took for the transition time. But that can, of course, be no longer than the age of the universe at that time. So electroweek translates to wave periods of between or many minutes, perhaps up to hours. You can also ask, well, we do have observational platforms for gravitational waves now on the Earth. They are observing gravitational waves of frequencies 100 Hertz, and that would in turn translate to physics at something around 10 to the 9 GeV. It's a very high energy scale. So those are the frequencies we should be looking at. And just coincidentally, these QCD periods and electroweek periods or frequencies are actually covered by current or future observations. Both are, which I'll talk about in a moment. So, as we all know, the era of gravitational wave observations is now nearly a decade old, and so ground-based interferometers of form of LIGO and now Virgo, and hopefully soon again CAGRA, are observing gravitational waves through a sort of Michelson or Fabry-Perot interferometer apparatus, which, as the gravitational wave goes through, changes the arm length, and you get a change in the interference signal, which you can pick up with a photodetector. So it's very simple kind of principle, but of course the challenge is in observing the changes in length, fractional changes in length of order 10 to the minus 21. And that's what was observed 9 years ago by both in two places almost simultaneously in North America. And here we have the picture of the strain signal that came through. Don't know whether you can see 10 to the minus 21. And that was characteristic of a merging black hole, a pair of black holes. And of course, since then, observations have continued, and various observation runs. So up to the third observation run, there were 93 confirmed events, mostly black holes, but one binary neutron star and one candidate black hole neutron star merger. And observing run 4 is underway until the middle of next year. And when I last checked last month, there were 147 detection candidates. So this is a very active and exciting field, particularly for astronomy and astrophysics. More recently, at the much lower frequency, nanohertz, so periods of a year, and that's where you might be wanting to look for signals of a QCD transition. Pulsars have been used as clocks in space to detect gravitational waves coming through between Earth and one of several dozen pulsars that are being continuously monitored by the various collaborations, in particular NanoGrav, but also the European Pulsar Timing Array and the Parkes Pulsar Timing Array. And gravitational waves cause the pulse arrival times to speed up or slow down relative to what they should, and these excess timing delays can be Fourier transformed and turned into a power spectrum. And so recently, there's been good evidence that there really is something in excess of all the other possible causes, and has been and particularly the angular correlation of these timing delays. So timing delays in a pulsar in one direction are anti-correlated with pulsars in 90 degrees to that direction, just because of the quadrupole nature of gravitational waves. So there's somewhere between 3 and 4 sigma signal of this particular correlation. So the leading candidate for this, if they are indeed gravitational waves, which most people are convinced they are, is merging supermassive black holes in distant galaxies. But that's the models are not quite giving the expected answer. So the expected answer is that this power spectrum should be minus 13 thirds, but the best fit is actually slightly different. And so there's been a lot of investigation whether there could be some extra physics going on, such as phase transitions at the QCD scale, or cosmic strings, or something else. So what can we say based on that about any stochastic backgrounds from phase transitions or anything else? So LIGO hasn't seen one. And so everything that they've seen is consistent with just detector noise. And so they say that at a frequency of 25 hertz, the gravitational wave power spectrum, which is the fractional density in gravitational waves relative to the total density in a logarithmic frequency interval. So it's a dimensionless quantity, and that is less than about 6 times 10 to the minus 8. Now, there is a detection by NanoGrav. So you can, and that's at a level of about 10 to the minus 10 at this frequency of around a nanohertz or a few nanohertz. And the NanoGrav collaboration has kind of looked at to see whether how well you can do by fitting supermassive black holes plus some other piece of new physics. And there's lots of new physics models, including phase transitions with sound waves, and these ones I think are cosmic strings or domain walls, and there are others as well. So that's very interesting, particularly for the QCD transition. So is it a QCD transition? And the answer is most likely not, because QCD, as you probably know, is probably at least at the low chemical potentials that we think were extant in the early universe at that time, i.e. close to zero. The transition is smooth. It's a crossover. So that is the pressure or the free energy on the lattice moves smoothly from something that's close to the Stefan Boltzmann from quarks and gluons down to something which is more like what you'd expect from a hadron gas of pions and protons and neutrons, and nothing. There's no discontinuity, no in slope or that can be seen. So very smooth evolution, no departure from equilibrium, no gravitational waves. What about the electroweak transition? As was shown in the 1990s, here in Helsinki, the Keijo Kajanti, and I see Kari's on the call, and I'm sure it's very familiar to you that the electroweak transition in the standard model is with the Higgs at its observed mass of 125 GeV is a crossover. So again, no discontinuities. There is a susceptibility peak, the Higgs susceptibility peak. You can see traces of a transition at about 160 GeV, the temperature, but that's as much as that's what happens. So this transition is sort of is very reminiscent of the liquid vapor transition in water, where if you replace the Higgs mass by pressure, you get a phase diagram which looks very much like the water phase transition. So at low pressure, you get condensation as you reduce in temperature, and at high pressure, you just have a very dense gas turning into a rarefied liquid. So this is what it looks like if you increase the pressure on a hot in hot water. So this is several hundred bar, by the way. So as you increase the pressure, the phase boundary becomes weaker and weaker, and eventually, as you say, it's just a uniform fluid. So again, standard model stays close to this crossover, stays close to equilibrium, no gravitational waves. So at that point, you might think, well, why should I think about first order phase transitions in the early universe at all? But I think most of us here are probably convinced that we need some kind of new physics to generate two big facts about the universe, one of which is the preponderance of matter over antimatter, and the other which is the existence of dark matter. So what that means is that if you're looking for phase transitions in the early universe, you're looking also for new physics that could have been and that the phase transition could have been a byproduct of whatever physics is giving you this extra phenomenology. Okay, so if we grant that there might have been a first order phase transition in the early universe, and that it might have generated gravitational waves, how do we look for it? And in particular, how do we look for it if it happened at around the electroweak scale? And again, the answer is by coincidence, provided in the future, so in the next decade, by LISA. It's a constellation of spacecraft, 3 of them. It's orbiting the sun a little bit behind the Earth, maybe 20-something degrees, and they are exchanging lasers around the triangle. The arm length here is about 2.5 gigameters, 2.5 million kilometers, and they are, by dint of clever technology, they are measuring the Doppler shifts between not precisely the spacecraft themselves, but between free falling test masses within the spacecraft. So then they can, fairly confident that they can measure relative changes in the Doppler shift or strains or relative distances in the distance, which you can get by just by integrating, of around 10 to the minus 21. So it's equivalent sensitivity to LIGO, and this in the range of a few millihertz. And what's there to be found are merging supermassive black holes. They'll be very loud. So here, this one here is 10 to the 6 solar masses, somewhere between 10 to the 4 and 10 to the 7 solar masses. It will be sensitive to those. Binary white dwarfs in our galaxies. So because they're white dwarfs, they're compact. They can get close enough to orbit with periods of minutes. Also, the precursors of the things that LIGO has observed. So well before merger, they have much slower orbits and are radiating at a much lower frequency. And maybe some kind of little bump with some characteristic frequency that's characteristic of the early universe, some first order phase transition somewhere around the electroweak or TeV scale. Now, LISA is not the only planned mission. There are two Chinese missions, Taiji and Tianqin, as well. Taiji is essentially very similar to LISA. There's also STIGO, a very sort of futuristic Japanese mission, which is not really off the planning stage yet. But I think there's a good chance that Taiji and Tianqin will fly next decade. So how do we? So one big strand of work, as Miha mentioned, is calculating the gravitational waves from first order phase transitions, and in all the work that's been going on that is not just me, but many people. We focus on. It turns out that there are certain sort of more or less thermodynamic parameters that you can identify in the phase transition, which are important for the gravitational wave spectrum. And first of all, there's the nucleation temperature and the transition rate. So that's the inverse time that the transition takes to happen. So this is a very active area, obviously, for QFT tunneling. That's exactly what you want to calculate, and that's what we want to hear from you. So so this beta parameter is something that you identify as the logarithmic, the rate of change of the logarithm of the nucleation probability per unit volume, the rate per unit volume, and it also controls the time which the universe switches from the metastable phase to the stable phase. Now, as it does so, the latent heat is released, and then so there's a parameter called the strength parameter, which is something like the latent heat. It's sort of a generalization of latent heat to out of equilibrium transitions. So it's the fractional release of energy divided by the total thermal energy. There's the speed at which the bubbles of new phase expand. There's the sound speeds in the two different phases, and an important part of the cosmology, which again relates it relates time to frequency in the gravitational waves, is the effective number of degrees of freedom of the plasma. Things are not very sensitive to that, but it's still there. And then once the transition has happened, you can identify sort of certain physical things about the fluid, and the fluid is generating the gravitational waves, which depend on these underlying parameters. So there's the kinetic energy in the fluid, and gravitational waves are proportional. The gravitational wave power is proportional to the square of the kinetic energy in the fluid. There's a length scale, which is ultimately the conveniently chosen to be the mean bubble spacing, or the spacing between the centers of bubbles on average. And then there's also the length of time that the fluid keeps moving. So these pressure waves keep propagating, and that's limited by the expansion rate and also how much energy there is in the fluid and the length scale of the fluid. So at the moment, there is a picture building up of a rather complex shape of a gravitational wave power spectrum, which depends on all these parameters. So, for example, you could imagine that. I'll detail that a bit more in the next slide. So here's a sort of a cartoon well, it's not more of a, it's more than a cartoon, but less than the final answer of what happens in an idealized system where the sound speeds are both 1 over square root 3, so you both have ultra-relativistic sound speeds, and that the transition is not too strong, and that the bubbles are not too big compared to the Hubble length. So that yeah, so this is what so the spectrum varies depending on whether you, in characteristic ways as you change. Well, let's do the simplest one first, which is the transition temperature. So the transition temperature sets the scale, the frequency scale, just through the fact that that sets the Hubble rate, and the Hubble rate sets the frequency scale. So just changing the temperature just slides the spectrum up and down. So if you change the transition strength, so that's increase the transition strength, you increase the energy liberated, so that increases the kinetic energy, and so that should increase the power of the signal. Indeed, it does. But you can see that that actually there's small changes in the shape as well, and that's a feature of hydrodynamics, which would be another. Don't have time to discuss too much in this seminar. And say the mean bubble spacing also changes the wavelength, characteristic wavelength, but actually it also increases the quadrupole moment of the gravitational. If you increase the mean bubble spacing, you increase the sort of the effective quadrupole moment of the fluid that's sloshing about, and so you actually also increase the power of the signal. And perhaps the most interesting thing is changing the wall speed, because that changes the shape of the compression waves around the expanding bubbles, and that makes a very big difference in the shape of the resulting fluid velocity power spectrum, and then also the shape of the gravitational wave power spectrum. Okay, and so what can we hope to observe in LISA of all these parameters? Well, just this is a sort of very rough preliminary investigation that I did a couple of years ago with a student, Chloe Gowling. And if the message is that if what these diagrams are supposed to show is sort of the relative error in these various parameters, so wall speed, transition strength, bubble size relative to Hubble, and transition temperature. And what it's saying is that if the signal is observable, that is, has a high enough signal to noise ratio, then the thing that you'll be able to measure most accurately is actually the wall speed. And that's because the shape changes the most with the wall speed. Okay, so that's lots of theory. Can we test it other than just by observing it? So, you know, we've got a lot of pieces that go from the fundamental physics to this gravitational wave power spectrum. It involves equilibrium thermal quantum field theory to compute the free energy, tunneling that you're interested in, or in, I suppose more precisely, it's either quantum tunneling or thermal activation. And they're needed for some of the parameters like transition temperature, transition rate, transition strength, and sound speed. So that the equilibrium thermal quantum field theory will give you those, or quasi-equilibrium, because I guess tunneling is not quite an equilibrium quantity. You definitely need non-equilibrium dynamics for the wall speed. There you go out of equilibrium. And then, of course, you need relativistic hydrodynamics to understand the fluid flows that result and their disappearance. So the question is there a laboratory system with a first-order phase transition which has some or all of these features that we can try and exploit and test these ideas on? And the answer is yes. There is. Well, there's more than one, but I want to focus on helium-3. And this has a lot of analogies with the standard model and beyond the standard model physics, in that ultimately the effective theory of low temperature helium looks very similar. So if you cool helium down, it turns into a liquid, it turns into a Fermi liquid. And excitations above the Fermi surface are fermions. Helium-3 is a fermion. They're quasi-particles. And if you cool it down to sufficiently low temperature, you discover that there's a pairing interaction, an attractive pairing interaction in the triplet channel. So what that means is that they form Cooper pairs, and there's an order parameter associated with that pairing, which, because it's in the triplet state, is 3 by 3, because it's angular momentum 1 and spin 1. So there's a 3 by 3 order parameter. So in an ordinary superconductor or superfluid, it's just a complex, but a complex number, a complex field. But here it's a complex 3 by 3, so 18 component order parameter. It's described by Ginzburg-Landau theory, as that's the effective theory, at least near the critical temperature for this superfluid transition. It contains lots of interesting extended objects, vortices, domain walls, other things. And there are also multiple superfluid phases. It's not just one superfluid phase. There's an A phase and a B phase, distinguished by symmetry, and they have a first order phase transition between them. Now, on the standard model side and beyond, there are analogies to make. So the analogy to quasi-particles of quarks and leptons. Well, we don't know about pairing interactions that form condensates, but maybe there are some. This is the physics behind Technicolor and composite Higgs. Well, in that case, the Higgs field can be thought of as a composite parameter, but it may be fundamental, but it's still a field. There's the analogy of the Ginzburg-Landau theory is the high temperature effective action, which has the effective potential, from which you discern the phase. That's the same thing basically as the free energy density, the bulk free energy density. In extensions of the standard model, there may be cosmic strings and other topological defects. And in extensions of the standard model, there may be multiple Higgs phases between which there are first order phase transitions. So many of you might know very well. So for example, if you add an SU2 singlet to the standard model, there's a wide range of parameter space where one or other of the Higgses gets a VEV, and there's a first order phase transition between them. So what do we know about this first order phase transition? So let's talk a little bit more about the bulk phases of superfluid. So as I was saying, it's superfluid, and the superfluid transition temperature is roughly 2 millikelvin, but it depends on pressure. So it's less than a millikelvin below at zero pressure, so zero gauge pressure, and at if you and up to 34 bar where it solidifies, then it's nearly 2.5 millikelvin. So it depends on pressure. This is and there are some symmetries involved, as I said, and the symmetries are rotation symmetry and also the spin rotation symmetry, and there's also, of course, the good old quantum mechanical phase. So the symmetry is even bigger than the standard model. So it's SO3 times SO3 times U1, but it's not a gauge symmetry. It's a global symmetry. And the stable phases that you get, so over most of the plane at zero applied magnetic field, the B phase, isotropic, which is an isotropic phase, is the stable phase. So this is what the 3 by 3 order parameter looks like. Here's the amplitude, which is measured conventionally in energy or equivalently temperature. So that's the stable phase over most of the low pressure in helium-3. But if you can go to high enough pressure, you discover there's another phase where the unbroken symmetry is product of two U1s, one spin and one combination of angular momentum and quantum mechanical phase, so corresponding to number density. And this is what you can. This is a representative example of what the order parameter looks like in the A phase. So this is anisotropic because it has distinguished vectors. An L vector, which is the in this case is in the cross product of the x. Whoops, sorry, and it points in the z direction. In this direction, the third direction. So incidentally, in order to theoretically predict the existence of the A phase, you do need to do a loop calculation. So, and that's of course in the jargon, it's called a strong coupling correction. And it's strong in the sense that this triplet pairing is order 1. All right. So what about the transition rate? So we can estimate in the way that we know well, which sort of one can trace back to some chemists, Kahn and Hilliard in 1958, or actually you can go back further. The idea is that you try and study the free energy of making a droplet of the stable phase in a big enough droplet of the stable phase inside the metastable phase, which in this case it would be the B phase below the transition temperature here. So you imagine taking the system, cooling it, establishing A phase, and then cooling it even further and seeing what happens. So then you, of course, know that the crucial thing is the energy of making a bubble just big enough that it can expand. So that's the critical bubble. And you can go through the standard calculation, which involves the interface, the interface surface energy, which you can measure, and the free energy differences. What you discover by doing this is that the crucial ratio of critical energy divided by temperature is, well, depending on which part of the phase diagram you're in, it's somewhere between 10 to the 4 and 10 to the 6. So at that point, you stop worrying about the prefactor, because e to the 10 to the 6 is such a big number that it doesn't matter what units you express it in, it's still the same number. So it's the same, basically it's the same number in seconds and in ages of the universe. It's still very big. So the prediction of the theory is that supercooled A phase lasts a very long time. It should essentially be stable. So what's observed? So you try and supercool the A phase, and this has been known for a long time. It doesn't last very long. It lasts for a few hours or multiple hours at most. So up here, so this is this is about an hour, and then up here, I guess we have multiple tens of hours. So what's going on? Well, how does this transition happen? What's happening? Well, of course, in an experiment, of course, it's not sort of a pure and infinite system like the early universe. And one of the early things that was understood is that if you bring up a radioactive source to the system, so here they brought up some cobalt for gamma rays and some thermal neutrons as well, you can increase the transition rate. So certainly, ionizing radiation can cause a transition. And even if you don't have a radioactive source, there are still sources of radioactivity. Your apparatus is probably a bit radioactive, and there are always cosmic ray muons to make lots of electrons. Now, what else? Well, there are boundaries. So maybe there's some physics at the boundary which makes the transition easier. Similarly, not just a boundary, but also there are some kind of topological or semi-topological configurations, perhaps at the boundary or even in the bulk, which might make the might seed the transition, make the transition easier. So all these sort of come under the heading of heterogeneous nucleation. And there are some other possible ideas that have been put forward as well. So boundaries certainly also come into the mix. In any experiment, it's rather difficult to eliminate rough surfaces. And in particular, there is always, unless you're careful, which I'll talk about in a minute, there's always the heat exchanger, the thing that extracts energy, heat from the helium and gives you the superfluid. And that is something with a very large area, and so lots of little pockets and rough surfaces. So actually, in a tiny of order millimeters cubed sample, the area of the heat exchanger might be many meters squared. So it could be that the rough surfaces are hiding something. There's some distortion of the order parameter of the rough surfaces, which are seeding somehow the transition. And this seems to be, but exactly what those seeds are is not clear. You can certainly control their number. It turns out that if you go through if your experimental protocol is not just cooling, but includes going from high pressure to low pressure, it turns out that a period of high pressure in the A phase can get rid of whatever it is or reduce the number of whatever it is that's being seeded. Okay, and so if it is energetic particles, what's going on? Well, there are two ideas about what's going on. One of which is the so-called baked Alaska scenario put forward by Leggett, and the other is the so-called cosmological scenario, which was inspired by the theory of cosmological phase transitions. So in both these ideas, the idea is that the energetic particle has forced the fluid to go normal in some region, and then they differ as to how the energy is transported away. In the cosmological scenario, it's rapid diffusion, so this blob just shrinks. And in the baked Alaska scenario, it's a ballistic quasi-particle. So you get a shell of high energy, of increased energy density, which keeps the system normal in a shell, rapidly expanding shell. But in both cases, the normal superfluid transition happens very rapidly, either outside the normal region or inside. And out of that mess, something happens which may be, and it's not quite clear what does happen. But the hope is that out of that mess is that if you're in the metastable region, B phase somehow emerges rather than A phase. Now it has to happen very rapidly because in this case, the A phase is out here. It's already established. It hasn't been disturbed yet, and so it wants to shrink and take over. But providing you can make a B phase region that's big enough, that is stable and will expand and take over. So trying to resolve this problem and understand the dynamics of the transition so that we can eliminate the possibility that actually there's something about tunneling we haven't understood is the project that we're involved in in the UK, Quest DMC, Quantum Enhanced Superfluid Technologies for Dark Matter and Cosmology. And the idea is to eliminate boundary effects by two different ways. One of which is making atomically smooth walls using the same technology that you make silicon chips with. The other is using magnetic fields. And one thing I didn't emphasize, which is that if you increase the magnetic field, an applied magnetic field, you favor the A phase, because the A phase is magnetic, the spins align to reduce the energy. So you can, if you have a region where you have a high magnetic field surrounding a kind of a region of low magnetic field, you can guarantee that as you cool the system, the B phase will only ever nucleate inside a region which is distinct from the boundaries of your experimental apparatus. And this is isolated from the heat exchanger, which is up here somewhere. The other way of isolating things from the heat exchanger is to use confinement. Again, if you have a very thin layer of helium-3, that again favors A phase. So if you construct, and I'll show you how to construct a silicon chip with A phase in only A phase, only B phase in a certain region. I'll show you in a minute. Here we go. So this is actually the plan of the system that we're doing, or rather our experimentalist colleagues in Royal Holloway are doing experiments. So here in the darker blue region, the depth is a few microns, but here in the lighter blue region, the depth is maybe 70 or 80 nanometers. And that's enough to make sure that there's only A phase here. So that's isolated from the fill line, which goes to the heat exchanger. So if the transition happens, it will happen in the dark blue region. And you detect whether the transition has happened with NMR. Again, because of the magnetism, the magnetization of the A phase, it has a different NMR signal. All right, so what do we get? Well, here's some preliminary data taken at 3 different pressures. And because, as I say, because of the NMR, there is actually an applied magnetic field. And so the transition temperature is just, AB transition temperature is just a little bit lower than the normal superfluid transition temperature. So we get these data points, so different pressures. So 22 bar is actually up here. So that's where the A phase region opens up. But nonetheless, as you cool down slowly, you still make A phase in this as you go through this narrow sliver. So this is the lifetime again, relative to one of the lakes. So you scale it by the volume of the lakes, and this is what you get. This is in hours, and you see these characteristic different shapes at different pressures. Now this high pressure is the same as was seen in the high pressure experiments that I showed you earlier from the 90s. But here's an interesting shape. So the lifetime goes down very close to the AB transition temperature and the critical temperature. And if you fit to your naive estimate of the critical bubble energy, and with just a couple of fitting parameters, E0 and a rate parameter, you get this curve here. So a very, very nice fit. But this E0 has got nothing to do with the temperature. It's actually roughly 10 to the minus 4 electron volts, which is of order 1 Kelvin, not a millikelvin. And this shape is very puzzling as well. It's kind of a little extra bump here. And also this attempt rate, the rate is difficult to understand as well. But we think it's got something to do with the radioactive particles that are being emitted from some potassium-40 in the experiment. All right, so how do we understand that? So supposing it is coming from energy injection. How can we understand what's going on, and also perhaps even simulate transitions, find some surprises in the transition. So we do that with by simulating with our effective theory, and the effective theory has a name. It's the time-dependent Ginzburg-Landau model. It has second-order and first-order time derivative terms, not isotropic, the derivatives, because it's not an isotropic system. There are vector indices as well as spin indices, so makes it, I suppose, a little bit unusual for a cosmologist. And there's also thermal fluctuations, which we can model with a Langevin noise. There's an effective math parameter which goes negative at the normal superfluid transition, and there are some quartic coupling terms. So these all collectively known as material parameters. And there are some boundary conditions which unlike in a cosmological simulation, you of course have to put into a simulation. So we've been trying to understand the dynamics of the phase transition and making some sort of preliminary simulations with a code which is built on a C++ lattice field theory framework called HeLa, developed by Harry and his collaborators. And we four have been working intensively in the Quest DMC collaboration to use the fact that Finland has got lots of nice supercomputers to simulate the system, because we have 18 component system. We want to simulate it in a large enough grid to be realistic. So here's a preliminary simulation, an example of one simulation that we did. This is a 26 bar. We're trying to model rapid cooling after energy injection. So at 26 bar, the critical temperature is 2.3 millikelvins. There's a small interval of stable A phase. And then once you get to 0.88 of the critical temperature, B phase is stable. The typical length scale, the coherence length of the system, so that's like the inverse mass, is roughly 12 nanometers. There's a time scale associated with this in this system, so the Fermi velocity is actually the velocity that one needs in these systems, not the velocity of light. So that corresponds to a time scale of about 0.3 nanoseconds. So let's see what happens when we make some A phase that we might get by quenching through the normal phase, and we allow it to equilibrate a bit, because the quench might be rather slow. Then we quench into the B phase at a lower temperature, and at a rate which is about 50 times the Ginzburg-Landau time scale. So this time scale is sort of the time scale of oscillations of the dynamical time scale of the order parameter. So this is sort of fast, but not too fast that we're outside the domain of the validity of the theory. And then there's of course some dissipation, which is not too dissimilar from the dissipation that's actually in the system. Then there's some details of the system, details of the simulation. So the differences between the simulations are, I'm going to show you two of them, kindly supplied by Quang, hot off the presses, is that either you stay for a short time in the A phase or for a long time in the A phase. And then you see what happens when you cool to the B phase. So this is what you get. And this is more or less the last thing I'm going to show you. So this on the left-hand side is staying a long time in the A phase. Blue means A phase and 0.86 temperature, 0.86 TC. And this is already gone. This went quickly into the B phase, and this is already gone. And this red color means B phase. And these are structures known as BB domain walls. It's actually B phase on both sides of them. And then finally, we do the quench, but this paler red means that we are still in the A phase at the temperature of 0.5 of a TC. Because what's being rendered here is the magnitude of the order parameter. And so as you change the temperature, that increases as well. But the magnitude of the B phase order parameter is bigger and therefore redder than the A phase. So this didn't go, but this one did. And it's kind of interesting to sort of try and see where it went. I haven't actually investigated this, but here you start here in the A phase, but you already see that some darker red is present as you go through the transition, and that emerges from the mess as B phase. So that's a very interesting result, and pointing perhaps to this cosmological scenario that I mentioned. Okay, so I'm running out of time, so I will just say that further work is needed. This is just preliminary simulations. We need to understand exactly what's going on. There seem to be seeds for the B phase left by a quench, but what exactly are these seeds? Is it pure B phase, or is it? And this relates nicely to we have seen other simulations where the B phase seem to emerge from some kind of junction of topological defects, and that links nicely with Simone Blasi's talk that you had last month. Yeah, so that's all I have time for and all I have to say. So I've tried to make a connection between using gravitational waves as a fundamental, as a tool to probe fundamental physics, to ultra low temperature physics, the physics of helium-3, because helium-3 has an interesting first order phase transition. The trouble is that the immediate analogy doesn't quite work because whatever bubble nucleation is happening, it's not obviously the homogeneous nucleation that we would like to test for the cosmological point of view. But nonetheless, it's a very interesting dynamical system which tests our ideas of the dynamics of these effective theories of scalars plus quasiparticles. That is what we'll be using in cosmology. And we certainly need, it will certainly help to understand this transition a lot better to improve reliability and of the early universe gravitational wave production. So thanks very much. I'll stop there.
Thanks a lot. Perfectly on time. So we have time for questions. Please raise your hand and unmute yourself when you want to ask a question. Okay, so we have Matthias Carosi.
Yes, thank you very much for the nice talk, first of all. So as far as I understand, in the plasma in the early universe is also rather, it must have some role, the fact that the species in the plasma are all relativistic. So of course, this is a feature that is not reflected, I guess, probably in the helium-3, right? Or I don't know, I wonder just how important is this feature and what would change?
Yes, yeah, thanks for that. So actually, as I hinted, relativity has yeah, as I say, it's not going at the speed of light, but the Fermi velocity plays a role which is kind of close to the role that the speed of light plays. So that's one comment. So another comment is that actually not all the species in an early universe phase transition are relativistic, because if they ultra relativistic, because if they were, then there wouldn't be a phase transition. So some species are changing their mass, and that's it's certainly true that in the B phase, all quasiparticles gain a mass. But I think that's sort of it's sort of certainly from some points of view, it's actually the quasi-particles which do gain a mass are the interesting ones. And ultimately, for the fluid dynamics, it's really just the equation of state of the fluid that plays the role. But yeah, there are. But the general point that there are big differences between the normal fluid that's still existing at low temperatures and the early universe fluid. In particular, in the A phase, there are it's anisotropic, and there are massless species, but they're only propagating the ones propagating along the L vector of the A phase, which I drew somewhere, but forgot where I put it. So does that go at least part of the way to answering the question?
Yes, absolutely. I was just wondering whether we could indeed understand some of those features, but I guess I understand it better now. Thank you very much.
Okay, so we have another question by Ian Moss.
Hi, thanks for the talk. That's very nice. I want to ask a bit about this seed business. It looks like these simulations are hot off the press, so I suppose they're still preliminary. But is this a feature of the quench? Is it very dependent on how you quench? Or is it just that in the initial A phase, you would always have some regions of B phase arising and then disappearing, and you're just catching one of these at the transition?
Yeah, that's a very good question. And actually, we don't know the answer to that question. But we have some ideas, and I don't know whether any of my collaborators are on the call. But I might invite them. If Quang is on the call, I might invite him to comment afterwards. But so the general point is that yeah, there are fluctuations in the A phase which are present just thermally, and here they are. You can sort of see them in these different different colored. Maybe I'll get going from in these different colored regions, but you can also see that that they have some structures in them as well. So it could be that actually in the thermal state of the A phase, there are already sort of the structures which will, when you quench, turn into perhaps B phase regions, or will become the cause of topological defects like domain walls or vortices. That we don't know. So, Quang, are you on the talk? Would you like to?
Oh, sure, I can say something.
Yeah, thanks.
Hello. Well, so sorry, I didn't notice the name of the question. Like the people ask the question, but okay, Ian, hello. So what you said is right, actually. The in the big range of the yeah, Mark, could you pause that here?
Whoop,
Yeah,
I just lost my mouse.
Yeah, it's yeah, go back to a little bit. Yeah, keep go back. Yeah, here. Yeah, pause at here. So you can see here what this region, if I put an annotation in here, this region and this region, you can see a very slightly dark blue region at here. Inside this region is a B phase, which freeze out from the quench, started from normal phase. So what happened in this very few frame of this movie, it was a normal state fluid was fastly quenched down to just lower than the A and B phase balance temperature, first order balance temperature, just lower than that. So in this case, you can see because it's just lower than that, then the B phase will have slightly lower free energy. So technically say the B phase actually is the absolute minimal phase. But the problem is the critical this kind of small B phase region didn't really match the size which necessary to match the critical bubble size. So with the system has damping, they are very fastly phased out, like just slowly shrink. If you Mark can play this video a little bit, you can see this region get smaller. If the temperature is keep in that very like just slower. If you focus on the left hand side, that region just shrink and disappear. Yeah, you can see the region start to shrink. Left hand side video. This peanut shaped thing just disappeared now. But if you reduce the temperature to absolutely lower, like the B phase will become such dominated minimal phase, this peanut will suddenly expanding because the size of this peanut of B phase just like the size is big enough for the critical bubble size of that temperature, which is 0.5 TC. That's why you can see the expanding and started the dark blue region, dark red region aggressively expanding because now this small peanut has bigger size than the critical bubble, and the bulk free energy of B phase is such lower, like probably 40% lower than A phase in this situation. So you get a very big latent heat. So it's suddenly start expanding very aggressively. This is what the rest you say in right hand side is the result of this expanding. So back to your question, what Ian Gass mentioned is right. The B phase has been seeded at the very beginning of this video by keyboard Zurich process.
Okay.
Thank you. So I think the next question was by Oli or Jonas, not sure who is asking.
Yeah, it's from me, Jonas.
Okay.
So Mark, you mentioned that you suspect that potassium decays are the reason for this quick nucleation. How does it lead to these weird lifetime curves that you showed?
Yeah, good question. If you've got an idea, please tell us. Yeah, the lifetime curves, where do they go? Yeah. So, well, so somehow that there is an energy barrier. You do need to make something that's bigger than the critical bubble. By when you inject energy, so the idea is you make a mess, and whatever that mess is, it does need to eventually turn into something that looks a bit like B phase, that's bigger than the critical bubble. So so somehow that probability is bound into the lifetime, and this critical energy does in fact decrease as you approach the critical temperature, because the free energy itself is decreasing as you the whole free energy decreases as you approach the A phase and the B phase together, relative to the normal phase decreases. So the whole scale of the thing is decreasing towards zero. But then suddenly you are actually not only are you approaching the critical temperature, but you're approaching the AB temperature. So then you get a competing effect, which is that the bubble is growing, and it's growing to infinite size. So, and that happens that happens faster in terms of parametric dependence than with temperature than the decrease in the overall free energy. So that's what this thing is, we think. But why it matches so perfectly to the critical bubble for energy in this sort of simple and not very well justified fit is we don't really know.
Okay, yeah, thanks.
Yeah, thank you. So the next up would be Thomas Bilam. Go ahead.
Hi, yeah, thanks very much for the talk. My question's also on this slide. It might not be quite fair because it might be an experimental detail, but you have these different lakes in the experiment, but your graph is all scaled to lake one, like lifetimes scaled to lake one. Did
Yes.
the experiment detect which lake the bubble is formed in?
It does, yes, because the different
Is
the different size lakes. Yeah, sorry, it's carry on.
Is the data from everything and then just
the data is combined from everything. That's right.
Okay.
Yeah. So these lifetimes come from many transitions which have happened in all the lakes. The nice thing about having multiple lakes is not only can you test the volume dependence, you can also, you don't have to heat up every time there's one transition. You wait for there to be 5 transitions and then you heat up again and cool down. So,
okay, and the surface area to volume ratio is different for every lake as well, I guess.
Well, that's a very good observation. The surface, you could equally say that it's scaling with it because they're equal thicknesses. You could also say that the rate scales with the surface area. We can't distinguish the two.
Okay. Thanks.
Okay. Good. So I guess we can wrap. Was there another question by Oli, or why is the hand up?
Yeah, am I allowed another question or?
Yeah, sure. Go ahead.
So my question was, is there a regime where you can actually expect theoretically to see bubble nucleation? You said this energy divided by temperature was 10 to the 4 to 10 to the 6. Like, can you tweak parameters or magnetic fields or something so that it's not 10 to the 4 to 10 to the 6, but instead 10, say, and then actually maybe observe it?
Probably not in this system precisely, to bulk A to bulk B, but I think Quang has some ideas about doing first order phase transitions between phases in confinement. So if you have a very thin layer of film of helium-3, new kinds of inhomogeneous phases emerge called the stripe phase. So you basically have a regular wave, regular distortion in the order parameter, and the transition between the uniform phase and the stripe phase is a first order transition for in some regions of pressure and temperature. So that, I think, is a possible, and there you can sort of tune things so that you get close to the spinodal point and accelerate the rate.
Thanks.
Okay. Good. Excellent. So thank you again for this excellent talk, lively discussion. Thank you everybody for joining in. And I should remind you that the next talk is taking place on December the 12th, and it's going to be given by Jonas Hirvonen. So I hope to see you there in about a month's time. So.
Well, thanks for the invite and invitation, and thanks for the question. And nice to see you, Ian. And
Yep.
Look forward to seeing you here.
Okay.
Mm.
Let me stop.